Hi guys, Luke here, and today we're moving on to silicon chemistry. Today we're going to look at Silyl enol ethers, which are pretty much storable enolate equivalents and, in inverted commas, enolate in a bottle sort of thing. We're basically just going to look at the synthesis of these enol ethers, and we're also going to look at sorry, let me get a comfortable position. There we go. We're also going to look at the reactions that they can undergo as well. There's obviously alkenyl silanes as well, and allyl silanes, which we'll look at in the next few videos. I'm not going to include them all in one because there's a lot of reactions for each. So there's a couple of ways of forming these Silyl enol ethers. First is by using a base, Et3N, and chucking that on the proton to form a double bond, and then pushing the electrons onto the oxygen there to form O-. Excuse the curly arrows, they're pretty nasty. Then the O- can attack the silicon, and because the Cl is less labile or something like that, I think it can go off and be a Cl- ion. The other way we can do it is by using LDA, which obviously also acts as a base. We've got the negative nitrogen, and it pretty much does exactly the same thing. Apart from this time, it can take a hydrogen from here instead. That's pretty much the only thing that's different. Or sorry, a hydrogen from there. So hydrogen goes from there, it goes up to there, that goes up to there, and that's how that goes there. So, as I said, there's quite a few reactions for this, so we'll just go through these one at a time. We can regenerate an enolate, starting with this alkene, cyclic alkene with oxygen and a silane on it, silicon on it, should I say. Write that with methyl lithium or TBAF. Obviously, methyl lithium can attack methyl lithium can remove that SiMe3 pretty much. That's exactly what it does. And then after that, what we do is we've now got an O-. Obviously, as you can see here, in this case we used F- in this step just to remove that, because as you can see in this step here, obviously it's stable when it's Me3 SiCl. Obviously this will be stable when it's Me3 SiF-. And that's the byproduct we've got there, NBU4. That's just one of the side products we've got from this reaction, the removal of this silicon group. And now we've got the O-. The O- can move its electrons down to form the double bond again, remove the double bond off here, and then this area can attack the double bond on this alkenyl bromine, which pushes off the bromine because the bromine is a good leaving group, effectively like an SN2, and that obviously just forms a reaction there. The bromine acts as an electrophile as well. The double bond of the bromine acts as an electrophile. The next is Lewis acid promoted alkylation. That's circled because there's an allylation as well, I think. Something like that. Maybe, I'm not 100% sure. If there is, we'll find out soon. Starting with the same product. Starting with the same starting materials. And what we're going to do is we're going to remove this chlorine here. Could just drop off by using the strong acid. Gives us a chlorine minus and a positive ion there. I'm not 100% sure why that's positive. Just need to make sure you know that it is. Obviously we've got the Cl minus, so that's obviously going to have to be have to have a positive charge there. But effectively, what we've got there is this here without the chlorine. The acid is needed to remove the chlorine so that we can use it in this step, and as in the last step where F- or MELI attacks the SiMe3, in this case chlorine does, so effectively we could do this in a couple of steps. We could remove the SiMe3 first and have O- and do it the same way we did last time, but we're going to attack it straight away in this case, and that attacks there, and then it's pretty much just the addition of alkyl group, hence the name of the alkylation. So as you can see, look, the arrows pretty much do exactly the same. So the arrows really from here should be going all the way over there. Shouldn't be pushing itself onto that bond there. The double bond, I'm not left-handed by the way. I don't know if you can tell. The left, I'm talking left-handed. Anyway, back up here. The curly arrow should be like this instead. Like this one down here. Anyway, that's that one. Lewis acid promoted aldol, here it is, it's literally the next step. Same reagent again. This time we're going to be using a aldehyde. The aldehyde can have a positive charge in it, whilst the titanium, partially binds, which is why the oxygen has this formally positive charge. That obviously removes or makes the trimethyl silicon bond break, and that forms a double bond again for our product. And then pretty much exactly as what's happened in the others, the double bond then attacks the positively or slightly positively charged, which obviously is acting as electrophile, the slightly positively charged aldehyde, which just forms this product here on workup, because obviously it'd be O- usually, moving the electrons onto the O there, but after workup we get OH as well. A few more reactions. There's this Lewis acid Michael addition now, so obviously there's another Lewis acid method. This case we're using dichloromethane, titanium with 4 chlorines on it, and this here. Different starting material this time. It's still a Silyl enol ether. And what happens this time is that we form this intermediate here. Now, I'm not 100% sure how you form this intermediate. Obviously, it's got something to do with this product here as well. I think what happens is that used to be the double bond. So the double bond breaks initially, and then must donate electrons onto this oxygen, and then the oxygen donates that electron onto the tin, which binds. Obviously, then the oxygen has a positive charge. The electrons must go up and down in this case, just so we form a double bond again in this product. And then we simply remove the TiCl with dichloromethane to form a lovely little intermediate there. Some say lovely, I say not nice at all, and that's pretty much what it is. But no, effectively what we do initially is get this to a minus and then add our phenol thing there. The tin chloride removes the SiMe, that goes down there, and then that can attack that, and that forms another bond, and that's pretty much how we get there. If that made sense. I'm not sure if that made sense or not. I'll try and say that again. So we've got the minus charge here, and the minus charge can then go and attack this silicon. I'll say silicon. And then that can move down to the double bond. The double bond can then attack one of the protons on here. Then one of the protons can go onto there, and yeah, I'm pretty sure that's how it'll work. In fact, the donate the double bond will just form the new bond there. And yeah, that's pretty much it, I believe. Something along those lines. And the next reaction is halogenation. Quite simple again, I think here. Si-Me3 spontaneously donates or breaks the bond in the presence of Br2, and then the same sort of thing happens. Again, fairly straightforward-ish. A little bit more straightforward than the other ones actually, halogenation. Because there's not much to it. That double bond breaks and forms another bond with the bromine. That's pretty much exactly what happens. And then the bromine leaves. Bromide leaves as another bromide minus. We can get the regeneration of enones as well as the regeneration of whatever we did on the last page. I can't remember exactly. In this one, we're going to look out for our copper organocuprates and obviously our silicon reagent as well. What happens first? The first step is that we remove our we add our R group, should I say first? First of all, we add our R group, that adds there, we get a minus charge up here. The minus charge then allows us to attract the silicon Me3. Obviously we've got a minus charge on there, minus charge will go down and kick off the chlorine. And then reverse of this pretty much happens in the next step. The chlorine then attacks the silicon, that donates its electrons back down to the oxygen, double bond. The double bond there goes and attacks the sulfur. Now I'm pretty sure, this is called sulfoxide elimination, and I'm pretty sure the double bond is the one that initiates this for the sulfur, and then the chlorine can go, and then the silicon can go as well, or the silicon does it spontaneously. But the last thing to go is the chlorine, effectively, because the chlorine takes off this. Basically, you just make Si-Me3Cl once again. Next step, we need to look for MCPBA as well, which you'll see in the next one, the next mechanism. But then we've got this product here. We use MCPBA and form an O- on this, which you'll see how in the next step. That O- pretty much cyclizes round, attacks the H facing backwards. That then forms a double bond in the middle, as you can see, and then that kicks off the sulfoxide. That's part of the sulfoxide elimination. And then we get a nice simple product there. Finally, for the Silyl enol ethers, we've got alpha hydroxylation. You see here, back to the original starting product, we use MCPBA this time, and this is MCPBA here, this molecule, that one there. What happens here is we have an alcohol group, the bond between the H and the O breaks by the donation to the oxygen double bond, and then the double bond attacks the oxygen. This bond then forms a double bond there, and that kicks off the oxygen up there. Down here, with the aromatic ring plus that, we've effectively got that now. There, we've got that now there, pretty much, that's that, I believe. And then we've got this product here, Me3 can get kicking itself off now, and we formed an epoxide there from that previous step, and we can start to break that up as well. the aromatic compound we formed down here, we're then using the next step once we've let the silicon do its work, and pretty much form a cycle which the O attacks the H to get its OH back. That then leaves this aromatic cycle, but then the double bond O can attack the methyl silicon, and then to remove this positive charge we add the electrons onto it there, and that forms our product. Plus we'll have methyl silicon attached to this as well. But yeah, that's a nasty mechanism for this one. That's quite a nasty mechanism as well. I'm not 100% sure of the steps. Just got to remember the curly arrows effectively. Obviously this can be a different type of Silyl enol ether. You just got to look out for the telling tales that it will be. So MCPBA, look out for alpha hydroxylation or the regeneration of enones, and then look out for our organocuprates as well, and obviously sulfoxide elimination for the regeneration of enones as well. Quite a tough one. Next time we'll go through alkenyl silanes and allyl silanes, I think.